Cool. Hello. Everything is fine. Don't listen to people who say things aren't fine, because it's not true. Everything is hunky-dory. Everything's going extremely well. Thank you for asking. So, how many of you have seen the announcement about the midterm? Okay. So, there have been complaints, and I have been forced to relinquish to my superiors a promise that at some point I'll fix the damn repos for you and mark the things that couldn't mark. But I have absolutely no idea when that's going to happen. It might be February. So we'll see how things go. It's higher priority that you should have an exam to write at the end of the semester, let's say. So that's how that is going. I don't know when it's going to be done. Who knows? We'll see. Maybe the TAs come back tomorrow and everything's fine. Somehow I doubt it. But you know, again, everything's fine. Nothing to see here. Move along, move along. There's no little man behind the curtain. So, anyway, let's talk about assembly programming. So we were dissecting this thing, which is our quasi-hello world program as expressed in assembly. Strings are difficult in assembly, as you might imagine, so the hello world does not actually compose the phrase hello world. It's just a very simple summing numbers routine. But, you know, it's still, I think, a good example. So, this is visual, with the UAL capitalized for some reason. Please go to Avenue, download Visual, the application, and you can enter assembly code here. And then, I know these are all cut off, but like there's execute, all right? And you can step forwards and backwards through the execution of these programs in a very similar manner to any debugging software. What's most interesting about the debugging, it's a bit like Python Tutor, actually. You remember how I was saying we have these 16 registers, which can be used for various things? Visual gives you, they're so important as to occupy half of the UI, right? These registers, these are the registers that you're viewing. You can view them in decimal, binary, or hexadecimal. You just click the thing. This is the status register at the bottom. You can tell it's important because it's been set aside. But yeah, when you run the thing, it'll tell you emulation complete. Incidentally, this is an emulator. It'll give you a history of the changing of the values in the register as the program progresses, which is very useful. What line number it was that wrote to it. In general, it's just a very useful system. The disadvantage is that it does not support the full complement of ARM instructions. So, you know, that's, you know, typically the type of price you pay for this sort of thing. In general, you would have to add more to this in order to run it on an actual ARM processor, right? But just for like learning how to work with data and learning control flow, this is enough for this class right now, okay? So, assembly programs are broken down by tab-separated columns. You can think of an assembly program as being like a table, right? So, first column is for the label. We talked about labels last time, but we'll go over them again. The second column is for instructions. The third column, fourth column, and fifth column are all for the operands to those instructions. Make sense? Once again, ordinarily, the first column designates the operand into which data will be placed if data is being calculated. For example, using an add instruction, R0 is where the data that's calculated will be placed. Using a move instruction, this is where things are being moved to. Quick review, things which, when you have a number that's preceded by the octothorpe character, otherwise known as pound symbol, and never known as hashtag, that designates an integer literal. Make sense? We're not going to worry about floats. We're just let's just stick to regular integer arithmetic that will be sufficiently complicated for the time being. Okay? Any questions? Yes, sir.
Could you have like a character after the octothorpe, and would that be a character, or would that just be like a number and say a base set is 510?
I don't know. It seems entirely likely that there would be an ability to specify hexadecimal literals and character literals. I'd have to look it up. Incidentally, in ancient times, this symbol used to mean number rather than hashtag. So if you sort of read it more literally like that, it's the number 10, right? So, thank you for your question. I'm sorry I couldn't answer it. Any other questions? Yes, sir.
Where can you go to download the MECHTRON?
It's on Avenue. This stuff here. So, Win is the Windows version, OS X is the Mac version, and then you've got two different Debian, I think those are like package manager files or something like that. Those are your things right there. That's how you get it. Cool? Yeah. And there it is in all its glory. I know that the print is tiny. There's nothing I can do about it, unfortunately. So, if we, you don't even, yeah, it doesn't even snap to Windows. Wonderful. All right, we'll do it manually. There we go. All right. So, for example, move R0, 0, move, actually I think, yeah, it doesn't matter if you capitalize. It's not case sensitive. R1, I think R's might be, I don't know. You can play with that and see if it is or not. Syntax errors, what? Valid source.
Maybe that's what's capitalized.
Maybe. Maybe it is, because maybe it does require capitalization. But it highlighted it green. Normally if it highlights, then it's fine. Alright, let's see here.
It's the commas. Do you need the commas after RO, R0?
Sorry, what was that over there?
The commas for next to R0, R1.
Commas? Oh, are there commas? Let me see here. Aha! That is correct. Alright, pardon me, thank you. Okay, you have to comma separate your operands. And just for the sake of everything being nice, let's tab it over anyways as well. There. Execute. So then we can step forward. You can see that the history of the, let's do the history of the this register, right? Stepping forwards. So it goes. Until eventually, you'll notice that, like, if you've been paying attention to the status register, it has been 0010 this whole time until the point at which R1 becomes 0, at which point it becomes 0110. That's important to branch not equals. That triggers that we're not branching this time, and that reaches the last line of the program, and it's like, okay, terminate, this program has now terminated. Make sense? Slightly? We're going to talk about the status registers. So, good, fine, excellent. So let's go through these operands. I know we already did, but let's do it again. The above example uses 4 different instructions. We have move, op1, op2, moves the contents of op2 into op1. C equivalent is op1 is equal to op2, semicolon. Add op1, op2, op3 computes the arithmetic addition of op2 and op3 and stores in op1. C equivalent is op1 is equal to op2 plus op3. So notice that the addition operation has assignment built into it. Assignment to registers. Subtraction computes the arithmetic subtraction of op3 from op2 and stores it in op1. The instruction is actually sub plus s, where s is the suffix that indicates that the instruction also sets the status register. This is necessary for control flow purposes. Equivalent C code. Op1 is equal to op2 minus op3. Branch not equals. Another compound instruction. Branch statements conditionally jump execution to the specified label. Incidentally, if you want an unconditional jump, it's just B with no suffix. The S suffix on sub S tells the CPU to also set flags in the status register for the instruction. The branch statement reads the status register and only executes the jump if the status register is in the correct state. If the condition is not met, control is not sent back to the label, terminating the loop. So this is why, like, do-whiles are more directly interpretable in terms of assembly programming than a regular while loop where you're testing the condition up front. Because testing the condition up front requires a jump state, an unconditional jump at the end of the loop back up to the test, right? And then a jump to after that if the condition comes out false. So you're jumping around the code more than with a do while loop, if that makes sense. With me so far? Good. So, In ARM architecture, there are 13 general purpose 64-bit, well, 64-bit or 32-bit, depends on the architecture, registers that can be interacted with. You can reference these as operands by name, R1, R0, R1, etc. There are also a number of reserved registers, such as the status register mentioned above. So when I say that there are 16 registers in total, the status register is one of those registers and is not, you cannot just plunk data into it. Well, you probably could if you wanted to, but why would you want to? That would be highly destructive to the program that you're trying to write to mess with the status register. So just leave it alone. Realistically, you probably won't need more than 4 or 5 general purpose registers. In fact, one of the things that, one of the optimizations that C, like one of the big, like the O flag optimizations on GCC, is to select some of your variables in your program to be register variables, but it only uses 4 registers for that. So even using that much still is enough of an optimization for that to be part of the O flag optimizations on GCC. Make sense? So, in ARM assembly, literals are prepended with the octo-core character. They obviously can't be written to, but otherwise function as you would expect them to. So, what were things like in the old days? I hear you had to compile things for different processors. Yeah. You had to compile code, you had to mail it to IBM. It took 4 to 6 weeks. Before garbage collection, data would pile up until the computer got full and you had to throw it away. Early computers could handle code fine, but comments had to be written in assembly. C could only be written on punch cards. You had to pick a compact font, or you'd only be able to fit a few characters per card. C++ was big because it supported floppy disks. It still just punched holes in them, but it was a start. That's, none of that is true, but funny. So, let's reject society's labels. Go-to statements in C are all that you have in assembly for control flow, as has been mentioned previously. Like in C, though you should never, ever, ever, ever do that in C, and anybody who decides to do that in C is getting lasered with my laser pointer. Not actually, of course, because that's actually dangerous, but you know what I mean. It's a thing you should never do, is the point. You can add labels to your code by simply typing the name of the label in the first column. You can either include an instruction on the same line or not. The assembler does not care. If you don't put one on the same line, then it just executes the next one, as you might expect. Leaving a space can improve readability, particularly if your labels correspond to code blocks, though code blocks don't really exist in assembly programming. You can still separate your code into, spans of continuous instructions with spaces in between. It improves readability, but it means nothing to the compiler. We can move execution to any label using the B or branch instruction. This is known as an unconditional jump. Make sense? In the previous example, we asked the subtraction operation to write to the status register if underflow occurs. So there you go. When you set the status register from subtraction, that's what it's setting. Does underflow occur, right? We then use a conditional jump to continue executing a set of instructions until such underflow occurs. This creates a loop. So if you want to avoid having to do this with the subtraction operator, you can manually set the status register with the CMP command, which is compare. So you can compare two values directly. You might be saying to yourself, then why did the previous example do all of this nonsense with the subtraction operator? Answer, this is precisely the type of optimization that you program in assembly to be able to do, right? The subtraction operator produces those values anyways. Setting the status register from it uses a side effect of another instruction so as to avoid using another instruction to perform that same functionality, right? So, more efficient programming, right? It takes no extra time to do sub S versus sub, and you have to use sub anyway, and that's faster than using sub and then compare. Make sense? The 32-bit current program status register keeps track of various pieces of information related to the execution of the current program. Much of this takes the form of status bits or flags. So the status register is filled with flags. Flags are individual bits that mean something when they're 1 and mean something else when they're 0, right? So we're entering the world where we are no longer dealing with whole integers. We are dealing with each bit in a register meaning something. This is something you'll need to wrap your brains around for 2TA4 in a big way, because that's basically how that's how configurations are set on GPIO pins on modern microprocessors. Cool? Yeah? Yes?
What do you mean by underflow?
When the thing you're subtracting ends up negative.
Okay.
So, or 0? I think 0. Yeah.
And so why is it being negative? Like, how does that tell the program to stop running?
So, the subtraction circuit itself, right? It has more outputs than just the number it's subtracting, right? In addition, you have to worry about overflow, right? Overflow occurs when the two things you're adding together, once added, are larger than the register you want to store them in, right? Underflow occurs in subtraction when the two things you're subtracting result in a number that's smaller than the thing you're trying to store it in. It's like it's overflowing on the other side. That's underflow, right? This is assuming unsigned arithmetic.
Okay.
Right.
Yeah.
So yeah. Certain bits are set by these circuits just, of course. And I don't mean of course to mean obviously. I mean in the course of their operation. We're saving that with the subtraction operation, all of the sort of extra bits that are flying around because of its, how the operation comes out. Does that make sense?
Yeah.
So, this is what the status register looks like. We don't have to care about any of these bits. We are only concerned with N, Z, C, and V. These are the important ones that control flow. N indicates that a value is negative. 0 indicates that an appropriate instruction produces a 0 as a result. Carry indicates that an operation requires borrowing, as in subtraction. And overflow sets if a result goes beyond the range of numbers that can be represented in signed to complement format. That's interesting. The rest of these are unimportant in this class. So, all right. I think the textbook that I was using to put these together is wrong, because it's not testing for underflow at all. It's just setting 0 if the result is 0, which makes a lot more sense. Because if we go back to the example program that we are examining, right? You see how it, like, branch not equals is, like, this one is the one that changed, and it's negative 0, and then the other two, and it's 0. 0 is the one that got set, because the result was 0. Right. So, so in ARM assembly, the B instruction has a number of suffixes which examine the state of the status register. EQ tests to see if 0 is equal to 1. NE is tests to see if Z is equal to 0. Greater than, less than, greater than equals, less than equals, negative, positive, minus, plus, all of these flags. There's a bunch more. Always execute it, never execute. I don't know why you would need never or always execute, to be honest, because you could just use B for always execute. But signed overflow, no signed overflow, there's just a bunch of them, right? They're all having to do with the various values in the status register. The way that you actually should program with this, when you're writing your program and you want to make a comparison and a conditional jump, write your program up to the point where you are making that comparison, emulate the program to see what the status bits are doing when the jump should be made, and then choose which of these is appropriate for that situation. I would not expect you to memorize this chart. Okay? I would not expect myself to memorize this chart. So I do not expect you to memorize this chart. Make sense? Okay, so let's examine this program. This is a program which reconstructs the if statement inside of assembly program. In this program, we take different branches based on whether R0 and R1 are equal or not. So we move 10 and 15 into R1 and R0. We use the, lowercase is totally allowed, look at this. So we use comparison, we compare R1 and R2. Branch equals on true, branch not equals on false. So branch equals jumps to this label, we then execute a move of 1 into R2, and then unconditionally jump to end if. False branch, we move 2 into R2, unconditionally jump to end if, and then we move 0 into R0 to indicate the end of the program. Does that make sense? To some degree? Should be reasonably straightforward? Yes?
Why does R0 equaling 0 make it end?
It doesn't make it end, it's just like, I don't know, when I was making this example, I guess I wanted it to do something after it was finished, you know? Rather than just have it end the program. Because like, what's the point of calling it end if it's like the end of the program? You should call it end program, right?
So what would stop it in this case?
Reaching the last statement ends the
Oh, so
program.
it's like compares one time.
Yeah.
This isn't a loop.
This is not a loop, this is
Right.
just an if statement, yeah. Yes?
How does the compare operator alter the status register for those branch statements to then make a decision on?
It's easier to answer that question if I load up the program. Oh wow. All right. All right, I guess I'm gonna have to just do it. Okay. All right. So, move into R0 the value 10, move into R1 value 15. If compare R0, R1 branch equals true, branch not equals false. True. It's important to point out here that true isn't a literal or anything, it's just a label with the name true. It has no semantic weight beside that. How is that maximize? Okay. I'm gonna see if I can drag so I can read the labels. So, here we are. We can see that for some reason it's starting us on line 2. There we go. So the value in R0 is 10, the value in R1 is 15. Notice that the status register prior to the call to comparison is cleared. It's all zeros. After comparison, the N flag is set, but the rest are 0. If we take a look at our thingies, we're Is the documentation lying to me? It seems like the documentation is lying to me. Because, like, this isn't the Z bit that's being set here. Goodness. So Z is, no, pardon me. No, I'm correct. This is correct. So, in this case, these two are not equal, right? Equality test to see if the zero flag is set to 1. So it would branch to true if that were the case. It is not. We fall through to not equals. Tests to see if the zero flag is 0. Therefore, it jumps to false. And that's correct in this situation because those two aren't equal. There. Okay, good. So, remember the second one is the Z flag. Z flag is 0. So, when we test branch not equals true, that is not a jump. But when we test branch not equals false, that is a jump, so we jump to false. We move 2 into register 2, jump to the end, and then terminate the program by overwriting R0 for some unspecified reason. Any questions about that? So, this program is not efficient. Yes?
So technically, the if label, is that completely unnecessary?
You could call it cheese.
You have to have it there.
No. It's never jumped to.
Yeah.
Yeah.
Sorry. It's just for formatting.
It's just, yeah, it's like, it makes it a lot, you'll agree, I think, that it makes it more readable.
Yeah.
Yeah, but
It doesn't actually
it doesn't actually
do anything.
do anything, yeah. So we're gonna talk about a few things that don't actually do anything, actually. So, number 1, The if label is never jumped to, right? So it's not even necessary in the program. So you can actually just remove it. Hop, 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 hop. Oop. There we go. Oh, wait, before I do that, I should do an example where they're the same, shouldn't I? Just for the sake of interest. So, if the two are the same, you'll notice that the status register gets set differently by comparison. We get 0, 1, 1, 0. The Z flag has been set to 1, so we jump it true to the true label. Yes?
What do the different columns represent in the status thing?
It's hard to see from where you're sitting, but it actually says NZCV right here. So that's N, Z, C, and V. Make sense?
Yes.
Cool. It would be better if they had like that information displayed more prominently, but this program was like some guy's master's thesis, so you know, no warranty expressed or implied. So this if label can be removed. In addition, line 5 is redundant, branch equals true. If line 6 doesn't jump to line 10, execution passes to line 7 anyways, right? So we don't have to have a branch statement that jumps over another branch statement that, you know, since they're exclusive, one executes or the other, then this would be normal execution anyway. So, and that means that you can also remove the true label because it's also at that point never used. Our program becomes ever shorter. The if and true labels are never used and therefore redundant. The jump on line 12 to line 13 is similarly redundant. It doesn't make a whole lot of sense to have a jump statement which jumps you to the next statement. That's how it works anyways. Right? So, we can save ourselves the hassle. Much shorter program. While this code is more efficient than the code on the previous slide, we've taken a major hit in terms of readability, particularly as the scallywag who wrote this code didn't leave any comments. Often, the purpose of writing in assembly is to perform these sorts of optimizations at the expense of readability. This is one of the reasons assembly has a reputation for being difficult and is used by a small number of people. Programming in assembly is hard. At one point in time, all programming was done in machine code, in assembler code. There are some stories from the ancient past, by which I mean the 1970s and 80s, of people who would write programs which were completely unintelligible to anyone who wasn't the person who wrote the program. Some of the old Atari games are written in this manner. Atari, by the way, all Atari games are written in assembly code. Yeah, there's this one particular humorous anecdote about a person who was developing software for like a video lottery terminal, and his boss fired him, and he was like, okay, fine, you think you can understand this? I'm leaving. So he left, and then they had to literally throw out all of the code and have somebody redo everything because nobody could make any sense of what he'd done. The better a programmer you are in assembly, the less readable your code is going to be because you know all of these little bits and tricks all of these, you know everything about every single command that you're using, like what it's doing to the registers, even the registers that are like auxiliary, and you can, you know, it's like that business with using sub s, right? If you know what subtraction is doing, you can use it to write more efficient code, but, you know, at the expense of readability. But nobody really normally cares about readability at the assembly level anyway, because, you know, yeah. Yes?
Can you comment on assembly?
Yeah. The comment character is semicolon. Yeah. So yeah, comments, but you know, the code itself is going to be almost unintelligible most of the time. So, good. So, rather than relying on the subtraction instruction to set the comparisons flags, we can use the comparison command explicitly with our earlier example. So rather than using sub s, we use compare r1 and 0, see if r1 is equal to 0, and then we go through the repeats process. I think you'll agree that's a bit more explicit about what's going on. But again, we have taken a 5 instruction program and we have made it a 6 instruction program. So we have increased the amount of time this thing will take to execute by 20%. Right? So, good. All right. So up to this point, we have been working exclusively with register memory, but other types of memory exist, of course. Over the next few slides, we will learn how to declare and initialize regions of memory, that is to say main memory, find the addresses of declared memory cells, load data from memory into registers, and store data from registers back into memory. We are going to have to use pointers for this. The key to understanding this process is that only registers may execute data manipulations, right? You can't specify a region of memory for an add operation. It must occur inside of the 16 registers of the CPU itself. C handles these procedures in such a manner that it looks like you're manipulating main memory directly, when that's technically impossible. So, you know, the process of programming language development has been a process of people deciding various things are too much detail for people to worry about, so we'll write the compiler in such a way that you don't have to deal with that directly, right? Going from C to Python, it was pointers, right? Going from assembly to C, it was interaction with the main memory, right? The concept of a variable in C, you know, people, when people like manipulate variables in C, they think that the thing they're primarily, they think the addition operation is being applied directly to the RAM cells, right? But that's not how CPUs are constructed, right? It has to be loaded into register memory first, then operated on, then put back, right? So when C was designed, it was designed to hide that fact, right? That's why when you specify a variable name, reading from that variable is implicit in where you put it in the line of code, right? If it's on one side of the equal sign, you're reading from it. If it's on the other side of the equal sign, you're writing to it. And that's just part of the semantic of the language. This is not something that's true in assembly language, right? Each of those operations, reading and writing from external memory, are specific operations that you are required to perform. Make sense? And I guess we'll talk about that at length next week.